In today's lesson, we're going to look at asymptotes and graph behavior of rational functions. So a simple definition of a rational function is a quotient of two polynomial functions. So here's an example, x to the third plus 1 over x squared minus 4. So if you look at just the numerator, that's a polynomial, and then the denominator is also a polynomial. So it's not just any function that has a fraction. For example, if we have like e to the x over the square root of x, neither of those are polynomials. So just because there's a fraction does not mean it's a rational function. This is specifically a polynomial divided by another polynomial. There's a lot in this unit that will sound familiar. We talked about vertical asymptotes and horizontal asymptotes in Unit 1. So this is just kind of a recap, but also a little bit of a dive deeper into what we've already talked about. So starting out, let's look at just vertical asymptotes. Now, rational functions can have a lot more than what we have here. We're just looking at some basic examples where there's one vertical asymptote, two vertical asymptotes, or no vertical asymptote. But there could be more than two, but in this unit, we're going to stick to these three examples. So if you recall back to Unit 1, vertical asymptotes are coming from the denominator. There's nothing to factor and cancel, so we're not dealing with any wholes. We're just looking at vertical asymptotes. So if we set the denominator, x plus 2 squared, and set it equal to 0, and now solve for x. We'll get x plus 2 equals 0, and then x equals negative 2. So we have one vertical asymptote at x equals negative 2. Because when you plug negative 2 back in, you create that 0 in the denominator, and that is why we have that infinite discontinuity. Okay, so now let's look at when we can have more than one vertical asymptote. So I always like to factor, just to double check here. We could take a 3 out, and then we'll have x squared minus 1, which would go down to x plus 1, x minus 1. And then denominator, x plus 3, x minus 3. So nothing cancels, so we can just take our denominator and set that equal to 0. So that means we will have two vertical asymptotes at x equals 3 and x equals negative 3. And now, what does it look like to have no vertical asymptotes? So here, let's look at this denominator. Nothing to factor either way. So 4x squared plus 1, if we set that equal to 0, we'll get x squared equals negative 1/4. And here, we'll square root it, but then we're square rooting a negative. There's no real solution. So what that means is there's no number that you can plug in for x that would create a 0 in the denominator. So if it's not possible to have a 0 in your denominator, then that just means there is no vertical asymptote. Okay, so now looking at horizontal asymptotes on rational functions. Horizontal asymptotes are either going to be, you're either going to have one or none. And I'll explain what these are here. So two possibilities of having one horizontal asymptote, or you could have none. Now, there are functions out there that have more than one horizontal asymptote. They just don't follow under this category of a polynomial divided by a polynomial. So somewhere on your notes, try to squeeze this on there. So I'm just kind of showing like a possible polynomial in the numerator and then one in the denominator. And I'm just looking at that leading term. And I'm going to use that to explain some horizontal asymptotes. So you have a horizontal asymptote at y equals 0 when, if you look here, if you look at n and m, when n is larger. So when n is greater than m. So here's an example. X plus 3 over x squared plus 3x minus 28. So as you can see, this has degree 1. There's a higher degree in the denominator. So when you have a higher degree in the denominator, that means that you have a horizontal asymptote at y equals 0. All right, next example is when m equals n. So if we have 3x squared plus 1 over 2x squared minus 5, we have the same degree, top and bottom. M equals n. That means that your horizontal asymptote is coming from those leading coefficients. So in this case, we have a horizontal asymptote at y equals 3 over 2. And then the last example is when we have no horizontal asymptote, and that is when m is greater than n. So if we have x to the third plus 2x squared over x plus 7, you can see the degree is higher in the top, so there's no horizontal asymptote. Okay, and the last part of this lesson is just putting the asymptotes into like discussions of graph behavior, specifically end behavior. Using that notation, as x approaches infinity, what does y approach? So for this one, let's make a note of the asymptotes that you can see. So let's see, there's going to be an asymptote at y equals 0 because there's higher degree in the denominator. And then there's a vertical asymptote at x equals 3. So now putting this into this notation. As x approaches infinity, y approaches 0. Here's a little visual. So we've done these graphs before. So now, what if x approaches negative infinity? Then y approaches also 0. It's approaching it, one is approaching it from the top, one's approaching it from the bottom, but they're both approaching 0. So now, bringing in something new, let's talk about that vertical asymptote. As x approaches 3 from the right, y is approaching, so I'm approaching the vertical asymptote. My y values shoot to infinity. But as x is approaching 3 from the left, y, so I'm approaching from the other side, it shoots to negative infinity. Okay, here's another example. This will have a horizontal asymptote and vertical asymptote, but I'm not going to talk about the vertical asymptote this time, just horizontal asymptote. So same degree, so there's a horizontal asymptote at those leading coefficients. So as x approaches infinity, x approaches negative infinity, they're both approaching 1/2. One will probably approach from the top, one will approach from the bottom, but they're still approaching the same value. But now, here's the last example. There is no horizontal asymptote, but can we still describe the end behavior as x approaches infinity or as x approaches negative infinity? So when there's no horizontal asymptote, this function, it's going down and it reaches that horizontal asymptote. If there is no horizontal asymptote, that just means that the end behavior might be doing something like this. It's going to infinity. And the other side, might be going towards negative infinity, or this could be flopped. So there's no horizontal asymptote, there's a different kind of asymptote that we'll be talking about in our next lesson. So I want you to think about actually plugging in infinity, a very large number in for x. So x squared plus 1, that would be positive. And then infinity minus 2, that would also be positive. So it's either going to be going, if there's no horizontal asymptote, the end behavior is going towards positive infinity or negative infinity. So for this one, it will go towards positive infinity. But now, if we're going to plug in a negative infinity, so negative infinity squared, oh, well, that's still positive, but negative infinity minus 2, that's negative, and a positive divided by a negative is a negative. So there's your full lesson on the rational functions, just looking at some basic vertical and horizontal asymptotes. Good luck with the lesson.